Hello, my name is Lindsay Broadway. This is Physics 2212, Experiment 3, Circuits. So the purpose of this lab is to observe how resistors, capacitors, current, and other aspects of circuits interact with each other in different scenarios. Some of the main models and principles used are the loop rule, so the sum of the potential, it will be zero in a round trip. The node rule, which is the sum of the current in to a node is the sum of the current out of the node. Ohm's law, which is the voltage is equal to the current times the resistance, energy conservation, and then some rules about capacitors and resistors in series or in parallel, which you can see in the bottom right corner in that chart. A preview of this lab is that the net potential difference will always be zero in a complete loop. The system is the ammeter or the voltmeter, depending on which part of the lab we're working into. The surroundings are the RC circuit, so it's just like different setup with different light bulbs or resistors or capacitors. And the initial conditions for most of the parts of this lab is that the circuit will always be closed with a different combination of resistors and capacitors. So the first experiment was to find the current when it's connected to two batteries. There's two resistors and two ammeters, and I predicted that it would be 0.02, and I found that the actual current was also 0.02, and when you flipped the ammeter, it stayed the same. And then when you changed the ammeter to a voltmeter, the voltage was 3, which is the 1.5 from each battery added together, and the current changes to 0 because the voltmeter blocks it, because the loop is not, or the circuit is not closed. So then I use the voltmeter on the closed circuit to identify the change in potential at each of these points. And when you add them all together, you get 0. And so that shows that the loop rule, the net potential in a loop will be 0, works in this case. And you can see on the graph in the bottom right-hand corner how the potential increases through the batteries and then decreases through the resistors, and it'll end and start at 0. The second part was figuring out the resistance of each of the parts of this ideal circuit. So for the 47 ohm resistor, I got 48 ohms as the resistance, and then for the 100 ohm resistor, I got 102 ohms. And then for the ammeter and the wire, it's 0 ohms because it is a ideal circuit. And then the reason that the current is 0.06 is because of the resistor in parallel rule, which is 1 over R is equal to 1 over the sum of the R's, which is shown here. And then another part was I connected the circuit to a capacitor and then charged it and then discharged it. So when I used a 10 ohm light bulb, it took around 8.3 seconds to charge and then 6.3 seconds to discharge. And when I used a 20 ohm light bulb, it took 9 seconds to charge, so a little bit longer, and 8.5 seconds to discharge. So you can see that it takes longer to charge and discharge when the resistance is higher on the light bulb. The final part of this lab was to look at the time dependency voltage across a circuit. So I charged a capacitor using a 9-volt battery, and then I removed the battery and tracked the potential difference across the capacitor. So as the light bulb was dimming, and then I tracked this in the spreadsheet on the right, you can see. So as the time increases, the voltage decreases, and then I use the equation given ln of V over V naught is equal to negative T over RC. And then I found the slope of that line to be negative 0.1672. So then you calculate the RC to be 5.98, which is very close to the theoretical value, which is 30 times 0.2, which is 6. And some slight errors here could be mistiming or rounding. So the what if questions mostly revolve around how would the circuit change in the real world. And for the first part, it would be because the ammeter does have resistance, so the RC value will be lower, and the voltage values would be lower because there is resistance. And then also for the battery question, it would charge almost immediately. It's almost instantaneous. But the prediction would not happen in real life because wires do have resistance, so the capacitor would take more time to be completely charged. So yes, this is Lab 3 circuits. Thank you.